Hey, do you remember how I told you how I'm gonna make a game where you can explore an ancient Mars civilization? Yeah, screw that, because I decided to spend the last couple of weeks to make a Halloween-themed minigame, because that's what successful game developers do all the time. Start a project and then, instead of finishing it, just start another one. However, I think this could be very interesting for you because I can teach you a lot of shader programming in Godot this way. The ground idea was to mix different colored ingredients together to get a magic potion with the wanted color. And I think at this point we need to talk about what color is and how it is represented in computer graphics. Because let me tell you something that may sound very conspiracy at first, but will make sense for you later on. Colors do not exist. Yes, that's correct. Colors are just an illusion your brain comes up with to process input of electromagnetic waves. That's what light is, electromagnetic waves. And one characteristic of a wave is its wavelength. Or in other words, how fast the top of the wave swings up and down. So you see, this is all just math and numbers, but your brain makes it into colors. A wave with this wavelength is red, a little shorter is green, and even shorter is blue. And even more shorter is ultraviolet. What you cannot see with your eyes, which is why I colored it in magenta. Magenta itself is also an interesting color because in contrast to every other color you can see, there is not a single wavelength that makes your brain see magenta. But to understand this, we need to go deeper. Your eyes detect the wavelength of light by using 3 different sensors. One that is mainly triggered by red light, one that is mainly triggered by green light, and one that is mainly triggered by blue light. Notice how I said mainly? That's because every light close to green, like yellow for example, will also trigger the green sensor, just not with the same intensity. Also the yellow light will trigger the red sensor just a little bit. So whenever a wave with a wavelength of yellow comes into your eye, your green sensor is triggered very strong and your red sensor is triggered not so strong. Your brain knows that must be yellow light. Bang! You see yellow. But this can be exploited to trick your brain into seeing colors that are actually not present. Instead of emitting one wave in the length of yellow light, you can also emit 2 waves, one very strong with the wavelength of green and one not so strong with the wavelength of red. The sensors in your eye have no possibility to see the difference in this, and so your brain thinks it must be yellow. In fact, this is how your monitor works. It's just an array of tiny bundles of red, green and blue lights that can emit with different intensity and make your brain think it sees all kind of crazy colors. We call this RGB colors. Now back to magenta. You remember I said magenta cannot be expressed with just one wavelength? That's because magenta is completely made up by your brain when seeing both blue and red light with the same intensity. Same goes for white. If red, green and blue all with the same intensity hit your eye, you see white. And obviously if no light at all hits your eye, you see black. Okay. You probably think, why do I need to know all of this? And actually you don't. All you need to know is there is RGB colors consisting of 3 separate values, and setting these values will result in colors, while all values to the max will result in white and all values to 0 is black. However, this model is just describing additive colors, so how colors are created mixing different wavelengths or lights together. In your everyday life you don't mix light together unless you are a photographer or a 3D artist. Which you might actually be, so this maybe makes my point invalid. But the average person is knowing mixing colors together more like mixing different paints together, or when cooking and mixing different colored ingredients together. You remember what kind of game I wanted to do? You can try it out yourself. Go get a red, a green and a blue can of paint and mix all of this together. And what you will get will not be white. In fact, it will be quite the opposite, a dark brownish gray something. That's because this is not an additive color model, it's instead a subtractive color model, meaning if you mix all colors together you will get black. Just think about it this way, the light you receive in your eye is not coming from a lamp directly, instead it is reflected from a piece of paper. If you have no paint on the paper at all, every wavelength is reflected to your eye. With every layer of paint you add to the paper, you will block some of the wavelengths of reflected light, and at some point there is no wavelength left that can be reflected, so you will see black. Like with RGB, this effect can be achieved with 3 different types of color: cyan, magenta and yellow. Hey, our old friend magenta is back. You remember how I said magenta is when you have blue and red light both coming at the same time? That's what we are doing here. Coloring a white paper with a layer of magenta will cause only the red and the blue wavelength to be reflected, so the green will be blocked. Coloring it in yellow will only allow the green and the red to be reflected, and the blue will be blocked. Coloring it both yellow and magenta will therefore block both the blue and the green, and will only allow the red wavelength to be reflected. So you see red. Nice! So we understand RGB colors and CMY colors. And now I can finally start explaining what I made in my game. Because the plan was to have a red, a green and a blue ingredient and mix those together to match a randomly generated color. We know for mixing colors in terms of cooking, we need CMY colors, but colors in Godot, like almost every other computer graphics software, are handled as RGB color. Thankfully, we can calculate an RGB value from a CMY set and the other way around very easily. The way I handled this is to create 3 different objects and assign each of it to a group. Red, green and blue. The object itself is of a type rigid body and holds the visual representation as well as the collision shape. Then I created an area the player can drop the colored object into. The area detects when the collision body enters and checks if it's from one of the colored groups. Now the real magic happens. The area is holding its own color in CMY. Whenever one of the colored object is dropped into the area, each of the 3 values is changed. For example, dropping a red object into the area will add 25 to M and Y, because red is achieved by mixing magenta and yellow, if you remember. However, since we would end up pretty quick with just black if we would just raise the 2 colors, I also reduced the 3rd color by 50. Of course, I had to limit the values to not get bigger than 100% or smaller than 0. I also added a white and a black object to give the possibility to create lighter and darker tones of a color. The only thing left is how we get Godot to actually color the object according to the CMY values. And for this we need to create a custom shader. Don't worry, this will actually be the easiest shader ever and basically a one-liner. First we need to select the mesh that should be colored. And then under Geometry, Material Override, we need to create a new custom shader. To create it under Material Override is very important, because on this way we can later access this via script. For now our shader is completely empty and we need to fill it with life. Every shader needs a type, and this will be a spatial shader, so the shader type is spatial. Now we need to define the fragment function. This function will be called for every pixel of the object that needs to be drawn. Here we can set the color. In Godot it's called albedo. You see this is getting a vector with 3 values. These are the RGB values we can set to a value between 0 and 1. If we set both the red and the blue value to 1, we see magenta again, just like expected. Cool, but we don't want to set the color by hard coding some values, so first we create something that is called a uniform. A uniform is something like a variable in shader language. We can set that even from outside the shader. We define it to be a vector 4, because a color can actually also have alpha value, but ignore this for now, and we name it color. With the statement hint color at the end of the line, we tell Godot this is a color and you can pick it. So if we go back to the object and select the tab Shader Parameters, we now see the just created color and can set it in the editor to any value we want. But we don't want to set it manually. Instead, we want to set it automatically based on the current CMY value of the magic area. Remember, a color in Godot is always in RGB, but like I said before, you can easily convert CMY to RGB. So in the process function of the magic area, we access the shader parameter with a material.materialOverride and call the function setShaderParam. Here we name the parameter we want to set and the value we want it to be. For the value, I call my custom written CMY to RGB conversion function, where I do the math. I think it's pretty self-explaining if you just think about it, but I blend in the formula for you. Just remember, one value in CMY will always block one of the RGB values and allow the others to pass. So now if we have an area that is green at the start and we start in mixing red object, it slowly starts transforming to yellow first before it gets completely red at some point. Great! Now our base functionality is ready. From here on, it's very straightforward. Create a player you can move around and that can pick up the color objects. Make a crystal ball that is randomly switching to a different color and check if the color of the magic area and the crystal balls are the same or at least close enough. Add points to the score if the color is matching. Reduce life every second the colors are not matching. Create an enemy that is randomly spawned and grabs a color object to throw it into the magic area, so the player must bounce away these enemies in order to prevent it, and start replacing all the placeholders with real models and start adding sound effects and music. And suddenly you have a game. If you're still watching, I hope you enjoyed the video. If you want to test my game, you can do it. It's uploaded to my itch.io page that I linked below. So happy Halloween or whatever time of the year is when you're watching this video, and see you soon. I'm still working on the mask game, I promise.